Welcome to QT Learning channel. In this lecture, we will discuss the 885 degrees Fahrenheit embrittlement. Description of damage. 885 degrees Fahrenheit embrittlement is a loss of ductility and fracture toughness due to a metallurgical change that can occur in stainless steels containing a ferrite phase, as the result of exposure in the temperature range 600 degrees Fahrenheit to 1000 degrees Fahrenheit. The embrittlement can lead to cracking failure. As illustrated in figure, when ferritic stainless steels are exposed to the temperature range of 600 degrees Fahrenheit to 1000 degrees Fahrenheit, fine, chromium-rich precipitates that segregate at grain boundaries. Grain boundary segregation of the chromium-rich precipitates increases strength and hardness, decreases ductility and toughness, and changes corrosion resistance. Sample of cracked material with cracks running through the grains suggesting severe embrittlement as illustrated in figure. Affected materials. 400 series stainless steels. Duplex stainless steels. Austenitic, 300 series, stainless steel weld metals, which normally contain up to about 10% ferrite phase, to prevent hot cracking during welding. Critical factors. The alloy composition, particularly chromium content, amount of ferrite phase, and operating temperature are critical factors. The lower chromium alloys such as 405, 409, 410, and 410s are less susceptible to embrittlement. The higher chromium ferritic stainless steels such as 30, 16% to 18% chromium, and 446, 23% to 27% chromium, and duplex stainless steels, 22% to 25% chromium are much more susceptible. Increasing amounts of ferrite phase in duplex stainless steels. Increase susceptibility to damage. When operating in the high temperature range of concern, a dramatic increase in the ductile to brittle transition temperature will occur. Duplex stainless steels also need to be cooled rapidly after welding to avoid formation of embrittling phases. Embrittlement can also result from heat treatment if the material is held within or cooled slowly through the embrittlement range. Affected units or equipment. Common examples include fractionator trays and internals in high-temperature vessels used in crude, vacuum, fluid catalytic cracker, and coker units. Typical failures include cracking when attempting to weld or to straighten bent, upset tower trays made of Type 409 and 410 stainless steel. This occurs often with vacuum tower trays of this material. Other examples include duplex stainless steel heat exchanger tubes, and other components exposed to temperatures above 600 degrees Fahrenheit for extended time periods. Please note that duplex stainless steels are normally limited to a maximum service temperature of 600 degrees Fahrenheit. Appearance or morphology of damage. 885 degrees Fahrenheit embrittlement is a metallurgical change that is not readily apparent with metallography. The existence of 885 degree embrittlement can possibly be identified by an increase in hardness in affected areas. Failure during bend testing or impact testing of samples removed from service is the most positive indicator of 885 degrees Fahrenheit embrittlement. Prevention mitigation. The best way to prevent 885 degrees Fahrenheit embrittlement is to avoid exposing the susceptible material to the embrittling range, or to use a non-susceptible material. Cracking of embrittled material can often be avoided through temperature controls during startup and shutdown. 885 degrees Fahrenheit embrittlement is reversible by heat treatment to dissolve precipitates, followed by rapid cooling. The de-embrittling heat treatment temperature is typically 1100 degrees Fahrenheit or higher, and may not be practical for many equipment items. Inspection and monitoring. This damage mechanism is very difficult to find prior to equipment failure. It is also time dependent and may take a while to develop in service. Online inspection is not applicable. Awareness of susceptible equipment can help direct inspection planning. The most effective method of detecting or confirming 885 degrees Fahrenheit embrittlement is removing and impact or bend testing a sample of the suspect material. Field hardness testing may distinguish embrittled from non-embrittled material, but hardness testing alone is generally not definitive. Related mechanisms to 885 degrees Fahrenheit embrittlement is sigma phase embrittlement. (885 degrees Fahrenheit embrittlement summary). Description: a loss of ductility and fracture toughness due to a metallurgical change caused by high temperature. Temperature range: 600 degrees Fahrenheit to 1000 degrees Fahrenheit. Affected metallurgy: 400 series stainless steel, duplex stainless steel and austenitic, 300 series, stainless steel weld metals contain about 10% ferrite phase. Prevention: use of low ferrite or non-ferritic alloys. Use of heat treatment followed by rapid cooling. Inspection methods. Removing and impact or bend testing a sample of the suspect material. Field hardness testing. Practice time. Question number 1. At what temperature of 885 degrees Fahrenheit embitterment takes place? Answer is A. Question number 2. Ferritic material exposed to a temperature of 780 degree F will have. Answer is D. Question number 3. 885 degrees Fahrenheit embrittlement is a loss in toughness due to a metallurgical change that can occur in. Answer is B. Question number 4. Which of the following can be used to confirm 885 degrees Fahrenheit embrittlement? Answer is D. This lecture is prepared by Samir Saad and this is his profile. Thanks a lot for watching and please waiting us for the next lecture.